We hear carbon fiber, and we immediately think of this invincible supermaterial, right? Lighter than aluminum, way stronger than steel. It's the stuff of dreams for supercars and spacecraft. But what most people don't see is the hidden complexity behind it all. A world where one tiny mistake can lead to, well, a total disaster. So today, we're going to pull back the curtain on the secret rules of carbon fiber.
Okay, so we've all seen moments like this, right? A material that's sold as indestructible just isn't. And look, this isn't just about a truck window. We're talking about critical parts in airplanes, in cars, in giant wind turbines. This isn't just some engineering headache. It's a super high-stakes puzzle.
And that really is the million-dollar question we're going to tackle. How does this happen? Well, the secret isn't really in the material itself. It's in a hidden set of rules about how it's all put together. If you get them right, you build a masterpiece of engineering. But if you get them wrong, yeah, you get spectacular, very public failure.
All right, let's get into it. The most important thing to get your head around is this. A sheet of carbon fiber isn't just strong on its own, not like a block of steel. Its strength is engineered, and it's built up layer by painstaking layer. It's more like a precisely choreographed performance than just a raw material. And if you want to know just how high the stakes are, just look at this chart. Over 60%, 61% of the entire market for this stuff is in aerospace and defense. So no, this isn't just for making fancy sports cars look cool. This is a cornerstone of our most critical life or death industries. Getting this right isn't just important, it's absolutely essential. So let's really get down to the fundamentals of how these parts are actually made. It all comes down to one concept, the stack, or as the engineers call it, the laminate. So any finished carbon fiber part is called a laminate. It's basically a sandwich of many super thin sheets, which are called plies, all glued together with resin. But here's the real secret. The final strength of that part has almost nothing to do with the raw carbon fiber itself. It has everything to do with how you arrange those plies. The material is just the starting point. And this diagram here shows you exactly what I'm talking about. You've got these individual layers, right? Labeled K. Each one has its own specific spot in the stack. And this is the crucial part, its own fiber direction. You stack them up one by one to build the final part. But there's a catch, a big one, and it's all about the direction those fibers are pointing. See, each one of those individual plies is unbelievably strong along the direction of its fibers. But if you try to pull it or bend it in any other direction, it's surprisingly weak. This property has a fancy name, anisotropy, and it's both carbon fiber's greatest superpower and its biggest kryptonite. So to manage this, engineers use a tool called a warp clock. Just think of it like their playbook. It lays out the key angles for stacking the plies. You've got 0 degrees for forces that pull, 90 degrees for impacts from the side, and the all-important plus and minus 45-degree angles to handle any twisting forces. This is literally how they tell the strength exactly where to go. But what if you need a part that's strong from every direction, not just one? Well, that's where a quasi-isotropic laminate comes in. The idea is to carefully stack plies in all 4 of those key directions, 0, 90, plus 45, and minus 45. When you do that, you create a part that acts a lot like metal, with uniform strength all across the board. And this is what that beautiful architecture looks like in the real world. That crisscrossing pattern of fibers, it's not random at all. It's a meticulously planned structure. It's designed to spread out any stress evenly, which makes the part incredibly tough and resilient, no matter where the force comes from. So the big question is, how do engineers build this strength correctly every single time? Well, they follow a very strict set of design rules. It's kind of like a blueprint for stopping failure before it can even start. Let's break them down. Here are 5 of the biggest rules for designing a tough-as-nails carbon fiber part. You've got to be symmetrical, be balanced, vary your angles, reinforce the outside surfaces, and have obsessive quality control. Let's dig into the most critical ones. Okay, first up, symmetry. This one is a huge deal. If you stack your plies asymmetrically, when you bake the part in the oven, it will literally try to tear itself apart and warp. But if you create a perfect mirror image layup around the center, you balance out all those internal forces. In fact, production data shows this one simple rule can slash the risk of warping by over 90%. Huge. Next is balance. The 10% rule is simple. It just makes sure you have at least a baseline of strength in all those core directions so the part isn't brittle. You also never want to stack more than, say, 4 or 5 plies all facing the same way.
That creates a weak spot where a crack can just zip right through. And finally, you always make sure to change the angle between layers to stop any potential crack in its tracks.
Now, having a perfect design on your computer, that's one thing. But actually making these parts in the real world, that introduces a whole new universe of challenges. And here, precision is literally everything.
You know, in the past, our ability to even check the final angles was pretty fuzzy. We were talking an accuracy of maybe plus or minus 10 degrees. But today, with advanced tech like ultrasonic testing, that has improved, well, dramatically. We can now verify the orientation of every single ply down to an accuracy of just plus or minus 2 degrees. That's an insane leap forward. And you might be thinking, come on, it's just a few degrees. Who cares? Well, in the world of composites, a few degrees can be the difference between a part that performs perfectly for 30 years and one that fails catastrophically on day one. Take a look at this graph. It shows what's called a failure envelope. The idea is pretty simple. Any stress that falls inside the shape is safe. The part can handle it. Any stress that falls outside the shape means the part will fail. So obviously, the bigger and wider this envelope is, the stronger and more reliable your part is. And this right here shows you exactly why those few degrees matter so much. That small yellow envelope, that's the performance you can guarantee with a 10-degree uncertainty. Now look at that massive blue envelope. That's what you get when you tighten your manufacturing precision to just 2 degrees. Better precision doesn't just make the part a little bit better, it makes it exponentially stronger and safer. A few degrees is everything. This constant drive for more precision is pushing manufacturing into a brand new era. We're talking automation, artificial intelligence, and a threat that almost nobody saw coming. I mean, the future is basically here. We've got robots placing fibers with a precision humans could never dream of. We've got digital twins and AI optimizing designs before a single physical part is ever made. Quality control is happening right on the production line, in real time. But all this automation, it creates a brand new vulnerability. Think about it for a second. In a factory that's totally connected and automated, every single action is controlled by a digital file. And that raises a pretty terrifying question. What if a flaw in a critical airplane part wasn't an accident? What if it was deliberate sabotage, introduced by hacking the design file and just changing a few ply angles by a couple of degrees? And really, this is the next frontier. As our materials get stronger and our machines get smarter, the weakest link isn't the physical process anymore. It's the digital code that controls everything. The secret to carbon fiber is no longer just in the layup, it's in making sure the blueprint itself is secure.